In the last video, I introduced to you a powerful new tool called Simpson's rule that helps us approximate definite integrals. And what I want to do is apply what we learned in the last video. I have Simpson's rule written out down here and apply that to an example. We want to approximate this definite integral here, and we're going to use Simpson's rule with 4 subintervals to do so. So why don't you pause the video and try working on this on your own? All right, assuming that you've given it a go, let's do some Simpson's rule. So first order of business here, we're going to use Simpson's rule and we're going to use it with 4 subintervals. 4 subintervals, and then we need to get delta x figured out. And we've already messed around with delta x in our other approximation methods, and it is the following. We have delta x is equal to the length of our interval that we're looking at, so that's 4 minus 0. And then we have over how many subintervals we're interested in. So 4 subintervals. So delta x is 1. That's pretty nice. And if we were to fill that in on our graph, that would look something like this here. Look something like this. These are our subintervals right here. Right here. Okay. And now that we have these, all we really need to do is look at what Simpson's rule is and just start filling it in for our function. So we found that delta x is 1, so we have 1 over 3, and then we're going to be multiplying by, we're going to have f of 0 plus 4 times f of 1, 4 times f of 1, plus 2 times f of 2, plus 4 times f of 3, and then finally plus f of 4. So that's Simpson's rule written out, and now all we need to do is figure out what these function values are. So we're going to have 1/3 times f of 0 is 6. We can just look at the graph here. Feel free to plug back into the function if you would like, but we have, and then plus 4 times f of 1, which is 3. 4 times 3. And then f of 2 is 2, so 2 times 2. And then plus 4 times, we have 3 again, 4 times 3, and then we have plus 6. So all we need to do is simplify here. We need to simplify. So we're going to have 1/3 times 6 plus 12 plus 4 plus 12 plus 6. And what is this added up? Let's see here. We have 24 and then 6, so that's 30. So this is 40, it looks like. This is 1/3 times 40, which is 40 thirds. So that's what we get out of Simpson's rule. And now I want to compare this to what the actual value of this definite integral is. So let's pull this definite integral down here and work on it and figure out what its exact value is. So definite integral from 0 to 4 of our function, and this is x minus 2 squared plus 2, and integrating with respect to x. So pause the video and try to evaluate this definite integral. All right. Here we go. We're going to use some u substitution to solve this guy. So we're going to let u be equal to x minus 2. Differentiating, we have du is equal to dx. And then our new limits of integration, when we plug in x is equal to 4, we get u is equal to 2. So that's our upper limit. And then our lower limit, we are going to have 0 minus 2. So that is negative 2. So our new definite integral under this u substitution is the definite integral from negative 2 to 2. And then we plug in x minus 2 is equal to u now. So we have u squared plus 2 integrating with respect to u. And now this is pretty straightforward. So this is equal to, we're going to have u to the third over 3 plus 2u. And then we're going to evaluate this at negative 2 and 2. So what do we get here? This is equal to, let's see, we're going to have 8/3 plus 4, and then minus, and this is going to be negative 8/3, and we have minus 4. And then summing these up, let me grab just a little more space. Summing these up, this is going to be 8/3 plus 8/3, so 16/3, and then 4 plus 4, so that's 8. Looks like we can get a common denominator of 3. So this is going to be 16/3 plus 24/3, and that comes out to 40 thirds. 40 thirds. So you can see our exact answer is exactly what Simpson's rule gave us. And why is that? You're like, oh, I thought this was supposed to be an approximation. It gave us the exact answer. Well, really, you just need to remember, what is Simpson's rule doing? What is Simpson's rule doing? Well, it's coming over here. And again, it's constructing some quadratic functions here. So it's going to be making a parabola. And these 3 points here that we're going to be constructing a parabola with, that Simpson's rule is making a parabola with, are along a parabola. So the parabola it constructs is exactly this curve that we have. Exactly this parabola that we originally started out with. And then it's just finding the area under this parabola for these 2 subintervals here. And then it's going to make another parabola for these remaining 2 subintervals. And again, these 3 points are on the original parabola that we had. So the parabola it makes is originally what we started out with. So it's going to be something like this. And then again, it's finding the area under this. So you can see Simpson's rule, this does now make some sense, why it gave us the exact answer. And in the next video, we are going to apply Simpson's rule to a non-quadratic function. We're going to be looking at using Simpson's rule to approximate a definite integral of a trigonometric function. And we're going to compare that with the other approximation tools that we've learned and just see how good Simpson's rule is.